Hello, everybody. Professor Nagy here. Today, we are going to talk about history of GIS, not to be confused with history of cartography, history of map making. So we're going to get more into kind of modern era of information systems, because that's really the influence here for the history of GIS. So it's really the beginnings of spatial analysis. Talk a little bit, not necessarily modern within the last 50 or 60 years, but kind of go towards when spatial analysis as a method of research kind of emerged in a rudimentary way. And so around in the 1800s, around 1825, Pierre Charles Dupin created the first choropleth map. So we've talked about choropleth maps and what makes them distinct. And it was first used to display social statistics. So more information about people and using a layering technique to be able to lay information about people on top of each other. And in 1832, Charles Piquet created a map representing the cholera outbreak across 48 districts of Paris. And that was later followed by John Snow, who used the same technique to depict cholera deaths in London. So the first choropleth map were the first inklings of spatial analysis to study social statistics was an early version of a heat map. Heat maps have become more common, and heat maps denote a density of activity in a particular area. And so not physics like density physics, but more of the density as we calculated number of things per square unit of some sort. For social statistics, it's typically by census jurisdiction or zip code or city boundaries or something like that in terms of a unit of measurement, and then different social statistics like income, education, in this case, instances of health problems. And so the use of spatial analysis predates information systems as we know it today, but is more of an exploration of how can we use maps as a way to verify or truth some of the information that we're trying to study. And in those, you'll see that there's some links in here that you can go to and read more about those particular cases or that particular topic. So now we're moving to early 20th century. A printing technique called photosyncography was introduced, and that allowed people to separate layers from a map. And the way that you can think of this is, I don't know if you've been exposed to this because you're younger than I am, but the use of transparencies to project an image of some sort. So this process of photosyncography allowed users to separate those layers so that they weren't all on one specific map, but rather 5 or 6 pages, let's say, of a map where you can turn the pages. There's a clear aspect to it so that you can look at different information on a map layered on top of each other. The technology meant different themes could be printed, but it didn't represent a full GIS since there was no opportunity to analyze the map data. Now, that's not necessarily true because you can visually analyze data. You can see where patterns occur if those things are mapped. However, you couldn't do it in a mathematical kind of way. So a very quantitative, statistics-driven type of method of analysis. Photosyncography didn't allow that mathematical part, but it still allowed you to be able to see those patterns. So pre-computer, kind of skipping some time there, but around the 1940s, 30s and 40s, you'll remember that in a history of maps, history of cartography, we know that maps were often used by the military as a way to denote territories, what kinds of things are happening in their territory, that the military in the United States was instrumental in collecting and preparing maps for those same purposes. In the 1950s, maps were simple, general reference maps, so think back to your map types. They had their place in vehicle routing, new development planning, and locating points of interest, but none of this was done on computers yet. One option that they had, one technology or method that they had was called sieve mapping. Sieve mapping used transparent layers on light tables to identify areas of overlap, like I mentioned, the projectors and the transparencies. But it calculated areas accurately. But calculating areas accurately was difficult because, again, you're just looking at a representation of information, right? It doesn't have, it's not layered onto, let's say, a coordinate plane or some sort of grid format. Even though we knew latitude and longitude, it's different. But calculating areas was difficult. The data was coarse. There was just lots of information, and it wasn't finely tuned in terms of spatial. Like, you didn't know where a line of delineation between a phenomena would stop and begin. Measuring distances was also cumbersome, even though we know about scaling and how to do that. Again, at that time, being able to do these things without the use of computers to put some parameters around it and keep it running more efficiently, and storage in particular, that's what made it cumbersome. You didn't have those things. So with all the issues that came with paper maps, cartographers and spatial data users wanted to explore computing options for handling geographic data. So you can see the amount of information led to, let's use computing options for all of this data that we have. And so in the history of GIS, this was the main incentive to shift from paper to computer mapping analysis, being able to do that in a mathematical, more accurate way, but also from the data storage aspect of, you have 100 paper maps. You can store that in a hard drive, for example. So how it saves you space in physical space, but takes up digital space. But again, how we viewed the novelty of being able to do that. And so we moved to the 60s. GIS was born. And so it started in the 60s as computers and early concepts of quantitative and computational geography emerged. Computational geography, again, is related to the mathematical computations of phenomena. You can also throw projections in there as well. Those are algorithms, and oftentimes they're tested through computational methods using information systems. Excuse me. Early GIS work included research by the academic community. Later, you'll find the National Center for Geographic Information and Analysis, led by Michael Goodchild, which Michael is the author of the article that I have to follow up on this particular lecture. He formalized research on key geographic information science topics such as spatial analysis and visualization. So again, being able to use some of the computer techniques or computational power and dynamics that were becoming available at the time. And these efforts fueled a quantitative revolution in the world of GIS, geographic science, and laid the groundwork for GIS. So again, this class is Introduction to Geographic Information Systems, GIS principles, but you'll see geographic science a lot, geospatial technology, different ways to describe phenomena that are related. Geographic science also includes the math of it. Geographic information systems focuses on the actual combination of cartography, maps, and spatial information married up with an information system. So again, we can see how we're going from cartography to information systems to hold, analyze geographic information. So that GIS, again, kind of thinking through GI, geographic information, IS, information systems, and putting those two things together. The first computerized GIS. So we have Roger Tomlinson. He is a pioneer in GIS, one of the first names that you'll see associated with the history of GIS. He started work initiating, planning, and developing the Canada Geographic Information System, also known as CGIS, in 1963. The Canadian government wanted Tomlinson to create a digital inventory of its natural resources using computers to merge natural resource data from all of the different provinces. So again, kind of a comprehensive approach, a comprehensive framework of geographic information that can be used by the government. Tomlinson created the design for automated computing to store and process large amounts of data. So he is an information systems pioneer as well. And that enabled Canada to start its national land use management program. Not to say there wasn't a land management program in place, it just wasn't as formalized because of the lack of computational power and storage that was available. Tomlinson also gave GIS its name. And so we can credit Tomlinson with kind of the onset of GIS as we know it in terms of a use not just for research, but more practical matters too. CGIS as the roots of geographic information systems. Again, the Canadian GIS is unique because it adopted a layer approach system to map handling. So it wasn't just we're going to prepare a map, but we're also we want to find ways of layering using that that sieving technique, but in a computer system. Now, because of if you've looked at a map of Canada, lots of square miles, right? Lots of territory. The idea for Canadian land inventory was developed in 1964. And so how do we take this idea of all of this spatial information and put it into a comprehensive framework? It didn't get fully operational for another 5 or 6 years, but that's because they were trying to figure out, Tomlinson and his team were trying to figure out how to do this work. So they were pioneers because there wasn't a method in place. They were creating it as they went along. What worked, what didn't work, so it was an experiment in itself. The Canadian land inventory used soil, drainage, and climate characteristics to determine land capability for crop types and forested areas. So being able to use the GIS as, again, a method of base data storage and being able to do analysis with that by using these layering techniques. So for Canada, they were interested in how land was being used, what can be used better for. So again, this led to GIS as a necessity for land planning and decision making. And again, kind of the onset of how can you not use a map and map data to understand your world. So, and for my planners in the room, you know, that's one of the reasons why this is something that's pretty significant in your line of work, being able to use maps, being able to explain things that are happening using maps, using it as a way to manage information, keep information up to date about your service areas. Back to the PowerPoint here. GIS pioneering. So following Goodchild and Tomlinson's work up to the 80s, that was the time period of GIS pioneering. So over these 20 years, they're trying to fine tune techniques. They're seeing advancements in technology, things like map graphics as outputs using line printers. So again, printers were just becoming available in a kind of mass production kind of way, becoming available to the public. And so the use of computers to prepare those things and then being able to print it out in a hard copy way. We know most maps are digital now, but again, at the time, the output, being able to show your client, here's what this looks like without bringing your computer along, without bringing them to the office to see the computer. Tomlinson was a US citizen, so going back and forth to Canada, that can be a bit cumbersome. So anyway, additionally, advances in data storage with mainframe computers. I've mentioned this a couple times, but spatial data, GIS data, things that are a visual representation of information, what you see on the digital map, that's some heavy data. That's a lot of file size, a lot of bits that are associated with that data. So as data storage started to become more prevalent, like we have access to this, then it became, now we have at least a digital repository for this data. And then lastly, recording coordinates as data input. So as you're creating your digital maps, being able to record coordinates on that. So again, kind of building a system of how do we even enter coordinates into a computer to make what we want. That's all being tested out and like, does this work? Does that work? But taking your coordinate plane and moving it to a software. That's what recording coordinates as a data output means. And these initial developments in the world of computing is what led to commercialization of GIS. Commercialization meaning it wasn't just available to experts. It was starting to become available to other users as well in the public. I'm going to go back in time a little bit for a moment to mention the Harvard Laboratory. So again, as Tomlinson is thinking about how to prepare the Canadian GIS around the same time, and also what contributed to Tomlinson's knowledge is the Harvard Laboratory. And so we have Howard Fisher, professor at Northwestern, created one of the first computer mapping software programs known as SciMap. So pre-QGIS, pre-Esri, ArcMap, pre-Mapbox, MapPoint, whatever, we have SciMap. In 1965, he established the Harvard Laboratory for Computer Graphics to be able to test out these computer mapping softwares, finding techniques. Some of the first computer map making software was created and refined at the lab. So again, the SciMap. It also became a research center for spatial analysis and visualization. And I'll say it was the first academic center for something like that. And you'll find that many universities still have these research centers for spatial analysis. We have one within the Levin College. It's called NODIS, N-O-D-I-S, the Northern Ohio Data Information Service. And there is a staff member, one of the emeritus faculty of GIS, that does research and analysis, GIS research and analysis for clients and partners. Yeah, many of the early concepts for GIS and its applications were thought about, created, tested out at the lab by a group comprised of geographers, planners, and computer scientists. And you can see how different specialties coming together to create something like this. So geographers, people that know the lay of the land, planners that know what is allowed to happen on land or to create administration and designation of land. And then computer scientists, how do we do this in a computing fashion? What's the software? What's the hardware? What are some of the data input techniques? How does this connect to storage? And now we have a lot more. We're seeing this now, that you see a group of people all within their respective expertise coming together and trying to figure out how to use GIS to study the things they know about. So this last point about geographers, planners, and computer scientists, that can be geographers, public health experts, and computer scientists. It can be government, public administration, and computer scientists and geographers. So don't get caught up in the planners are the only ones that use this, because you've seen 1,000 uses of GIS. And many of you are coming from a variety of disciplines, archaeology, planning, general urban studies, public health, environmental sciences. I don't know if anybody from public safety is part of this, but you can see how all of us together, knowing what we know, and then being able to use a GIS to display that, how powerful that is. In 1969, Esri was founded. They are the largest proprietary software for GIS. ESRI is the company, Environmental Systems Research Institute. They make the ArcGIS, ArcMap products, which you'll learn about in the next class. Jack Dangermond is the name to remember, affiliated with Esri. He was a member of the Harvard lab that we just talked about, and him and his wife founded ESRI together. They started out as a consulting firm. That means that they provided mapping services and analysis through contracts. So people would come to them, they say, here's what we want to do. Esri would say, hey, we can do that for you, it'll cost this. And so as a consulting firm, they applied computer mapping and spatial analysis to help land use planners and land resource managers make informed decisions. But again, we think back to some of the first examples of spatial analysis being public health. How do public health experts make informed decisions? How do public safety management professionals make informed decisions? That maps can be that. As we develop many of the GIS mapping and spatial analysis methods we now use, regardless of what actual software you're using. And these results generated a wider interest in the company's software tools and workflows. Workflows are, how do you get from here's all the data that we have to here's a analysis I want to execute. What are the steps in that process? That is the workflow. And these are now standard to GIS. Again, it doesn't matter what software you're using. Those are kind of the nuts and bolts of a GIS. I want to talk a minute kind of off the beaten path, but back to kind of GIS as a tool for analysis and how different experts have used mapping and spatial analysis in GIS in their work, and brought GIS more to the forefront as how can you not be doing something like this when you're studying land patterns. And so Ian McHarg pioneered the use of map overlays to highlight natural features that commonly included flood zones, wetlands, woody vegetation stands, slopes, drainage, aquifers, areas under cultivation, and included man-made features. The way that he did this was each asset, meaning each asset of flood zones, wetlands, woody vegetation stands, each of those is an asset, would be assigned a value. So I want you in your head, think about a table, like an Excel table. And each asset, so I have in my first cell, wetlands. And in my second cell, I'm going to give it a value, let's say 1 through 6. And depending on how the public rated these different assets, those would become the hierarchy for these overlays. And so physiographic features were cataloged as separate maps, and then McHarg would then overlay these to create a composite map illustrating these different obstructions. That was part of his design method. Ian McHarg is Design with Nature. Areas containing multiple features would appear as the darkest, again, the density, and might be valued more than lighter color areas. So as you see more density of information on top of each other, that might be through this process something as really important to consider, that we have a density of activity in this particular space. Is it something that we want to change, or is it something we want to retain? And McHarg came up with the 4 M's: measurement, mapping, monitoring, and modeling. And GIS allows a combination of mappable attributes. I think, I have never run out of space in my GIS. So when they say limitless combination, I think that's very true. It's just a matter of how much processing power you have available to you for all the data in your project. The combination of mappable attributes to be arbitrarily weighted, meaning you come up with what that weighting system is. You're not following any particular prescription. And electronically combined to create hybrid maps, which are simply spatial representation using the Earth's surface as their datum, and human input as to how do you value those things. A little bit more about national GISs. So now we know about the Canadian GIS. Let's move to another part of the world, the US and the UK. We have the US Census Bureau as early adopters of some of the core principles of GIS, and being able to display those social statistics. So again, think back to those cholera outbreaks and the beginning of using maps as a way to display social statistics. And so we have the Census Bureau that led to the digital input of the 1970 census using the data format GBF-DIME, which stands for Geographic Base File Dual Independent Map Encoding. Less important that you know that specific term, but more of, hey, we're going to start mapping social statistics using this available mapping system that's out there. And so this particular file format supported digital data input, error fixing, and even choropleth mapping. So again, pretty sophisticated at the time as a result of the creation of this file format. I want to stress when we are thinking about GIS that they are a specific type of file format. A lot of spatial data is multiple files in one. We'll talk more about that when we get there, but I just want to kind of point out this idea of a brand new file format to hold spatial data. Just like your .docs and your .xls and your .pdfs, that this was the creation of a file type to be able to manage geographic information in a system. And using this format, the US Census Bureau began to digitize census boundaries. Digitize means taking from like a paper map and making it digital. So digitizing the boundary lines and the features of those paper maps. They began to digitize the census boundaries that we have over the country. And census boundaries are going to be something that you would encounter a lot, particularly with social research. If you're trying to measure density and patterns, these units that we talked about, these units of measure a municipal area that's bounded. Let's say a lake that has boundaries. I mean, a lake's a bad example in this case because we're talking land, but um, um, census, the census has three types of geographies. They have census tracts, they have census block groups, and they have census blocks. And those are in kind of order of importance there. Tract is the biggest, block level is the smallest. Block groups are kind of what it sounds like, kind of in the middle. They're a collection of the block level stuff into a new unit, not quite as big as a tract, but a group of the smallest blocks. Again, I mention this because that is a unit of measure that was now becoming more widespread and available for people to understand because we don't see those census boundaries in the real world around us. And so they also digitized roads and urban areas. And this was a huge step forward in the history of GIS because, again, we're using a national data platform, the government, adopting a technology for its work. Also, the Ordnance Survey in the UK started using their routine topographic map development. And in 1976, the USGS publishes its first digital elevation model, and that is a computer map with relief, so 3D, in response to the high relevance that this type of data now had in the context of geographical analysis. We wanted to measure the depths. So think back to when we were talking about horizontal datums and vertical datums. The digital elevation model adopts a vertical datum as well. So we're leaving the 80s and we're talking about GIS going commercial. And as computing became more powerful, Esri improved its software tools. Just like as we have new methods and new findings, they are coming across different ways to improve their software and the methods of analysis. Working on projects that solved real-world problems led the company to innovate and develop lots of GIS tools and approaches that can be broadly used. And that means that it doesn't matter what discipline you are, you could use the same method of analysis, the GIS and some of the GIS tools of processing, no matter what you were studying. And so Esri's work gained recognition from the academic community as a new way of doing spatial analysis and planning. And again, it's the public's access to being able to do this. In need of analyzing an increasing number of projects more effectively, Esri developed ArcInfo, the first commercial GIS product. And that was something that I used when I first started out. Less important that you know about it now because it's not, ArcInfo is not around anymore as we knew it from the beginning. And when you start to use Esri software, you're probably not going to encounter this at all in the certificate program. But it's important that that was the name of the first commercial GIS product, was ArcInfo. Note ARC line as part of that name, ARC. Anyway, if you don't get that, think about the name, the term that represents a line when you're talking kind of digital cartography. It's called an ARC. The technology was released in '81 and began the evolution of Esri into a software company, a multi-billion-dollar software company still today. Over the last 20 years, 30 years, the importance of spatial analysis for decision-making was becoming more recognized. I took my first GIS class in 1996, and that was when, at that time, GIS was only a specialized offering within geography. And then I was in an undergraduate planning program, and that program adopted GIS as one of its software requirements. We also had a requirement of learning CAD, computer-assisted drawing, AutoCAD, but that was soon replaced by GIS as our primary software tool. So again, kind of dating myself a little bit, but just wanted to share some experience there. GIS was being introduced to classrooms and companies, and software was able to handle both vector and raster data. We'll talk about vector and raster data later on. I'll give you a little snippet now, though. Vector data is based on, again, coordinates. It is points, lines, polygons, shapes that you see on the screen. And then a raster data is more picture type data, satellite imagery, photography, and it's more pixel based, grid based. Again, we'll talk about those things more in another section, session, but this was the beginning of vector and raster data combined into one software. You used to have to use specialized softwares to view both. You still have specialized softwares for raster data because that gets into a little bit more of remote sensing, and that there are some specific softwares related to remote sensing, but you can input raster data, like load those files in, and you can do raster analysis. So again, this was the beginning of, you could do both. So with more satellites being launched into orbit, this data collected from space could be consumed into a GIS, which is the raster data. And so spatial data accuracy changed from the size of an airport, meaning that was your margin of error, to the size of a small shed. And that's being the introduction of raster data into your GIS to validate and verify location points. GPS now has led the way to great innovative products like car navigation systems and unmanned aerial vehicles, and in your phones, your smartphones, right? So GPS is now kind of part of our everyday life. It didn't used to be that way. And I think oftentimes people might confuse a GPS with a GIS. GPS is global positioning system. So again, we'll talk about this more in geospatial technologies, but GPS is not a GIS, because you cannot analyze things. It is, here's where you are, and here's what's surrounding you, but you can't analyze that. Some might think that, if you were using GPS to be able to get from point A to point B, that is a type of analysis. And I suppose arguably the provision of distance can lead to an analysis of, if I want to go 4 or 5 places, I want to analyze the distance or the best route of that. But that's going a step further than, here's where I am right now, here's where I'm trying to go, and this is going to route me in that direction. But it does give you options, right? Do you want the shortest route? Do you want the scenic route? Do you want no freeways, no bridges, things like that? Anyway, moving on. Democratizing GIS. So again, making it, putting it in the hands of more people. GIS data has become more ubiquitous. That means that my mention of like how easy it is to access maps and spatial data through your smartphone or your devices, that's what it means what this means by more ubiquitous. It's accessible to download for free. Anybody can get to it as long as you have access to the internet. I suppose that's a barrier. Online repositories like ArcGIS Online store massive amounts of spatial data, and it's a matter of quality control and fitting it for your needs. Quality control is, how up to date is it? How accurate is it? Who's reviewed it lately? Are they an expert? It's kind of like doing a Wikipedia analysis where you look up something using Wikipedia and then you look down below to see what references were used for that. And you're like, how good of an entry is this if I only see one reference, for example? So quality control, this is the metadata, who collected it, what date, and the citations that you'd put on a map product. The range of commercial GIS software products out there seems endless these days. Esri is really kind of a foundational system from which other things have been built, though. So I'll share that. Is, again, Esri was the first GIS, commercial GIS, and so many people saw the opportunity to build something on top of it that is kind of a proprietary app that goes on top of ArcGIS or Esri or QGIS or whatever GIS that you're using. The main shift of is of GIS users building their own GIS software in an open collaborative way, thus QGIS. So this software is made available to the public and it's called open source. And the big plus is that they are for public use at no cost. The catch is, how do I learn it? And here we are. Open source is becoming mainstream today. We gradually entering an era of open source GIS software, and more light is shining on QGIS than ever before. We've had partners out in the field asking if we're teaching QGIS, they want to be able to use it. But as the cost of GIS becomes prohibitive, then you have some open source options. So there's always going to be a place for commercial GIS software, no doubt about it. People are going to hire other companies for their services. Software companies like Esri provide solutions to practically any spatial problem that exists today. And you can find, again, smaller proprietary products at cost to do specific things that you want to do with respect to spatial analysis. We also have the advent of computer systems. I've kind of alluded to this throughout our talk. Advancements in GIS were the result of lots of different advances in technologies. Databases, the creation of like an Excel, like a database system that can be complementary as a way to hold attributes of spatial information. So when you're not looking at the screen of the picture of the map, again, what is the metadata that's behind what you're looking at? Being able to use databases and developments in database technology. Computer mapping, again, just being able to put maps in digital form. Remote sensing, the availability of satellite imagery. Programming, literally being able to code, being able to create these different software tools to use. And that is also an avenue for you to explore in your GIS training. Is we don't do programming as part of the certificate because that does get into a little bit more of the computer science. But as we see in job postings, a lot of job postings are asking for some basic programming for introductory or entry-level positions. So know that if you don't want to be a computer scientist, that's okay, but you may have to learn some computer science techniques. Advances in geography, again, with the types of information that we can collect through satellite imagery, being able to update our geographic models, like our geoid and our spheroid and our datum. Mathematics, what are the mathematical algorithms and calculations that we can use to study these phenomena. And then computer-aided design, I'd mentioned AutoCAD. Computer-aided design is more kind of structural. It's less related to land, but things need to be built on land, right? Even if it's in water. So there is a relationship between GIS and CAD. I think of CAD as more for more specific structural things, like actual structures, buildings, roads, bridges, things like that. But you're finding more of a way that you can seamlessly transfer data between CAD programs and GIS programs, and some that you can do both. The evolution of technology. I've mentioned a couple of these already, but just to emphasize, the main areas that have had a major influence in shaping GIS as we know it now are graphical outputs, data access and storage, and data input. For graphical outputs, the capabilities of computers to generate graphical outputs have greatly improved for screen rendering or for the case of printed outputs. So again, just our computer graphics. The tools that we have available to us for computer graphics and the graphics of GIS are really important. It's a visualization. So being able to have graphics as a visual is integral to a GIS. Data access and storage. The size of GIS data sets has increased enormously, and it's going to keep growing, and it's going to be married with other data. And using these large data sets would not be possible without corresponding improvements in both data storage and data access. One of that is cloud, the availability of the cloud now for us to be able to hold data, also to be able to host data if you were using a website or some other web tool to disseminate spatial data. And data input. In the early days of GIS, data were manually digitized. Again, kind of tracing or eyeballing paper maps and putting them as digital lines, digital arcs into a coordinate system software. Now creating data requires specific hardware such as high resolution scanners or specific software such as the one used for automatic digitalization of pattern recognition based on images. Uh, Less about the automatic digitalization of pattern recognition. What that means is you know a pattern exists and you can create a representation of that pattern on the paper, on the map. So being able to take things and that you can now use photos like plat maps from like the 1900s, and you can use some of those photos as part of your overlay. You can use raster and pixel-based images as guides for matching up boundaries, matching up cross points, things that help you orient different layers of a map. Data sophistication. And so this is important, and data is just unavoidable in GIS land. You're just talking about data all the time. But the launching of the first Earth observation satellites represents a key advance. And so the techniques that were already in use for aerial photography developed mostly during the First World War. And again, as I mentioned, the role of the military in some of our first US maps and maps in general were applied on a global scale when the first satellites were created. We have different techniques associated with satellite imagery. Excuse me, subwater. Um, we have different techniques such as LiDAR now, which started around this time, that can be used to get elevation data with much more detail. And that opened up a lot of new possibilities for areas such as terrain analysis. LiDAR came on the scene in the 60s, again, because that's when we were launching our satellites, and became widely available in the 80s. So it was kind of private data for a couple decades. And then as GIS became more commercial, then it became more not commercially available to us, but available to us for free. We have the Spot Image, the first commercial company to distribute satellite images that covered the entire globe. That was created in 82. In 81, GPS became completely operative for military use. And then in 2001, we see it more widespread in the market with us using it. Its accuracy for civil use was increased, us using it as civil use. In 2000, elevation data from the Shuttle Radar Topographic Mission is released to the public, and that covers about 80% of the Earth's surface with a resolution of 1 arc second. Again, an arc is a line, and think about our degrees, minutes, seconds. We have 30 meters related to a second. We have spatial data infrastructures that are developed as a result of all of this new data is coming on the scene. The most relevant of them is the U.S. National Spatial Data Infrastructure. That was created in 1994. And many of these activities and developments follow the specs set up by the Open GIS Consortium, the OGC. New data sources are always coming on the scene. You could create them, you can find them. Somebody, comes up with the next view into spatial data, and the amount, precision, and quality of data that's now available in a GIS has dramatically increased. Spatial theories and techniques. Once the first GIS was implemented and could respond to the data management and analysis needs for which they were created, new techniques and approaches began to develop. Going back to mention Ian McHarg again, he defined the basic ideas about map overlays. They're fundamental for the analysis and visualization of geographic data layers within the GIS. We've talked about Ian already. We have terrain analysis, another field that has experienced a huge qualitative change because of GIS. Again, the introduction of elevation. So traditional terrain analysis is mostly based on geology and geomorphological analysis. That developed into a quantitative science focused on the morphometric analysis of relief. So again, being able to introduce quantitative methods to analyze terrain. Along with the analytical component, cartography also evolved in the context of GIS. Now we have a computer system that can hold all this stuff, and now we can do editing, right? We can see, oh, something's new, something's changed. So our methods of quality related to cartography are being informed. In 97, so we had talked about Ian McHarg. I want to mention Myron Orfield. And he presents population patterns using GIS, really kind of the first time in a pretty significant way. And in 97, he published Metropolitics, which is it is the most widely cited GIS analysis of population demographics. And what do we know about population patterns or being able to access social statistics? We know that the US Census Bureau started doing that in the 60s. And so we have Myron Orfield that is taking the work of the US Census Bureau and mapping those social statistics for other uses. So again, accessing data, making it available for people to consume and understand and present in terms of their research and their findings. The advances in CAD applications and in-screen rendering techniques. Rendering is how fast can it make that graphic. That's rendering, how fast your computer or how accurate your computer can render a picture or render a visual. It helped in defining a new discipline, which is computational geometry. And that is the vector data, computational geometry. GIS vector analysis is based on that. Understanding our points, lines, and polygons, how they fit onto a coordinate plane. And there's also another way that you can use GIS, and that is something called PPGIS, public participation GIS. You can also say PGIS, public GIS, and it's an ongoing effort to democratize GIS and public decision making. And that means that that there are public forums that are using GIS as a method to collect, present, understand, and analyze public problems. Like we want to build, we have in our neighborhood or our city, we have the opportunity for a new development to happen. We're going to hold a public meeting and we're going to take a look at our community to see where that development might fit according to the parameters that you have in place for development. Let's say maybe we need to do some work on a watershed. Let's identify the riparian zone of that stream or river so that we have a better sense of our boundaries and our service area. And PPGIS is just a mode of using GIS that involves the public in making sure we're all on the same page and that we understand the situation and the plans for moving forward. And also, we've heard the word or the term big data a lot. I think that's really the next frontier in GIS is obtaining, managing, and cleaning millions of data records. Millions of data records, also known as big data. Much of the data is now collected via online crowdsourcing. So we are mapping things that are provided through crowdsourcing campaigns, but also social media check-ins, for example. So this assumes that GIS professionals should have at least a basic understanding of data collection methods, like where are you getting your data, where does it come from, how do you download it, is it in the format that you need, verification of accuracy, who has put this data together, who is the owner of it, are they reputable, is it up to date, is anybody maintaining it, organizing it and making it accessible to users. So if you've got millions of data records, billions of data records that are out there, how do you organize those things into something that makes sense? How do you chop it into pieces that make it workable and usable? And how do you compare that to other data sets? And kind of a question, what other skills would we need to implement these types of GIS solutions? I think that, remains to be seen. And the more we see different professionals working together using GIS as a method for storing, presenting, altering, analyzing, that, there are soft skills too, communication skills, project management skills, your ability to understand data sets that you're working with. So some content knowledge or expertise about the types of information that you're working for in context. So I think that there's a lot of possibilities. And one of the things that I really enjoy about this class is that there's students that come in from so many different backgrounds. And I think that's part of the fun is seeing how you start to think about how GIS can be used for the types of stuff that you do in your major, in your research, but also in practice. You know, when you go and get a job, how is GIS used in your field? And there, one thing I'll say is you can never know every single thing about every single GIS. It's just not possible. But again, we know concepts, we know theories, which lead us to a lot of the answers for things that are, gosh, I had no idea. And I'll share with you, there are new developments in GIS every day that I haven't used yet, and I probably won't use them until I have a reason to. So I think just being open to, GIS is not done developing, that it's going to continue to change and evolve. But again, I think a lot of the cartographic, geographic, and information systems concepts and ideas are part of more of the exploration of the possibilities. And if I was in a situation in which I was going to use GIS or consider using GIS, what are the other considerations that I have? So that was the last slide. I hope that you enjoyed this talk, and I look forward to seeing you next time.